Welcome to Module 3, Sound Level. In this module, we will explore the quantification of sound, focusing on how we measure and perceive sound intensity, pressure, and power. Sound can be quantified in several ways. So first, sound power, which is the total energy generated by the sound wave. And second, the sound intensity, which is the acoustic sound power per unit area. Sound pressure, which is the force exerted by the sound wave on a surface. Understanding these quantities is crucial for accurately measuring and interpreting sound in practical scenario. So this is specifically true for sound pressure, which we'll be using the most. Our perception of sound sensation follows a logarithmic trend relative to sound pressure. So for instance, let's give an assumption, a sound pressure of 1 unit, 1 U. This corresponds to a sound sensation of 1 unit, 1 U. We want to double the sound sensation to 2 unity, so the sound pressure needs to reach 10 units. So now, if we want the sound sensation at 3U, so the sound pressure needs to reach 100 U. So finally, if we want the sound sensation at 4U, then the sound needs to reach 1000 U. Moreover, in acoustics, often the sound is measured in comparison with other sounds, not as an absolute measure. For example, the sound pressure can be measured in comparison with the air pressure if the propagation medium is, of course, the air. In acoustics, we call this as level. So now let's try to combine the two elements. And the decibel is the answer. Decibel, dB, is a scale that represents the sound level by incorporating our logarithmic perception. By comparing sound powers or pressures, we use a reference point, typically the threshold of audibility. This makes the decibel scales effective for describing both physical sound and human auditory response. Well, from the mathematical point of view, given two sound powers, W1 and W2, where W2 is a reference power, so the formula for computing the sound power level is L1 equal to 10 log W1 over W2 in decibel, which is actually a logarithmic level. Now, sound pressure level is instead a practical measure because sound pressure is easier to quantify directly with respect to others, like the power. So we know that power is the square of pressure. So let's try to transform the power to the pressure. We obtain that LP, which is the pressure, is equal to 10 log of P1 squared to 2 over P2 squared to 2, which is actually 20 log P1 over P2 decibel SPL according to the properties of operation of logarithmic. In order to provide the sound as an absolute pressure level, we use the atmospheric pressure, as we said before, which is the threshold of audibility. And we use it as a reference pressure. So LP is actually in this case equal to 20 logarithm of 10 Pascal over 20 micropascal decibel SPL, which is actually 114 decibel XPL. So now, since it is difficult, very difficult, to have an intuitive reference on the loudness of a sound corresponding to a certain amount of decibels, so I would like to provide here some decibel values for the typical sounds, like, for instance, chatting or car sounds, city sounds, and so on. Let's give now an example taken from music production. Maybe several of you has experience in music production. So if an input signal equals the output signal of a processor, so the SPL's difference is 0 dB. This is the reason why often volume faders or knob, like the one in the figure, have scale going from minus infinite dB SPL to 10 dB SPL, where 0 is the optimal value. Now, doubling the sensation equates to a 3 decibel increases, which is kind of a standard. So this relationship between sound perception and decibels provides a standardized way to describe audio intensity. So let's prove it from the mathematical point of view. So let's consider the sensation S2, which is actually in decibels since it's a sensation. It's equal to 10 log S2 over S0, which is actually 10 log 2 multiplied S1 over S0, which is 10 log 2 plus 10 log S1 over S0, which is actually 10 log 2 plus S1, because 10 log S1 over S0 is nothing more than the sensation S1 in decibel. So the final result is 3 decibel plus S1 in decibel. So now let's look at some practical examples. We would like to discover the relationship between the distance and the SPLs. So let's consider to have a speaker that produces 115 decibel SPLs at 1 meter. At 6.1 meters, the SPL decreases, as can be intuitive to consider, and this is due to the spreading of the sound waves, of course. So now let's ask to ourselves how many decibels we will have at 6.1 meters. So let's consider the formula. SPLs, it's equal to 115 minus, and we use the formula with the 20, so 20 log 6.1 over 1 decibel. So which is basically 115 minus 15.7, which results as 99.3 decibel. Second, power reduction. So a speaker with an electrical power of 1 watt produces 115 decibel SPL, as before, as the example we have done just before. And this is a distance of 1 meter. If now we reduce the electrical power from 1 watt to 0.22 watts, what will be the SPL still at 1 meter? So now we decrease actually the power of our system. So the formula is the SPL is equal to 115 minus 10 log of 1 over 0.22 in decibel. This time we use the formula with the 10 because we are dealing with powers. And the result is 115 minus 6.6, which is actually 108.4 decibels. Now, what is going to happen if we combine two sounds? So, for instance, we have a couple of noises running in the room, and we would like to know the amount of power of those sounds in decibel SPL. So in order to do it, we need to use logarithmic addition properties. So LP1 plus LP2 in logarithmic operation is 20 multiplied 4 log of 10 powered to LP1 over 20 plus 10 powered LP2 over 20. On the other side, if we have 2 power instead of 2 pressures, so the same formula is applied using 10 instead of 20 before the logarithm. For example, if we have a fan and an air conditioner that produces respectively 60 dB SPL and 55 dB SPL of noise, the total noise is calculated using the logarithmic formula that we have seen before in order to account for their combined intensity that, as you can understand, is not the direct sum, but the logarithmic sum. So applying the formula we have seen before, so the result here is 63.87 dB SPL. So this method helps engineers and scientists predict the overall sound levels in environments with multiple sources. Now, to conclude, in this module we have covered how sounds levels are measured and perceived, focusing on the relationship between physical quantities and human sensation. This foundational knowledge is pivotal for understanding more advanced topics in acoustic and audio processing, and we will use this information later on in the next modules. So thank you for your attention.